technical lecture. Teaching ends end of next week, and next week Nived and I will be here, and we are basically doing a questioning session. So you can ask us questions, things that are unclear, that need to be clarified. So one of the homework assignments, so to say, for you is prepare questions if you have questions, because we both will be here. If you have anything which has stayed unclear to you, which we have covered in the course over the last 13 weeks, then feel free to ask us next week, ask questions. It's your lecture. If we are done after 20 minutes and no one has any questions, we're happy to depart, and you can go home and we can go back to work. So it's your chance to use it and ask us questions. So that's what's happened next week, and this week is the last technical part of the course. So over the last 2 weeks, Nived introduced the problem of classification. That means we actually want to assign semantic labels or label information to data points. And today we are doing something which is related to this, but different. Today we are looking into grouping similar data points. So this is something which is typically referred to as clustering. And the main task is basically we have measurements or other types of data, and we want to, for example, simplify the data by grouping things together which are similar, forming groups. Those groups do not necessarily need to have as a label or a semantic label as it was the case in the classification lectures. And we typically don't have training data at hand. We just try to group them so that similar things are together. And there are different approaches that exist, and we will cover a few of the, let's say, most popular ones that can be applied for solving this type of problem. So why is this relevant? Just kind of one example. For example, you have an image and you want to group similar regions in an image. So let's say you're flying with your UAV, or you get a satellite image, and you have an image taken from above of a ground surface. And what you see in this image, you can see basically the intensity values in the background, and what you see additionally are those black boundaries. And those black boundaries are basically regions which the clustering algorithm has identified of being similar. So whatever is in one of those has a black parameter, like this one over here, means actually the thing in here seems to be the same. And you can already see that this is a simplification of the original image content, because you can see that in all those areas here, you see actually slight variations in color. So saying just whatever, all the pixels which have a certain intensity values belong together would not be a good measure for this type of clustering. So you may allow some variation in the intensity images, and you can clearly see that certain regions are perfectly extracted. We can see here in this case the ground, or the ground cover is different. There are some areas where we see, okay, this could also be the same field, for example, over here has been split into 2 parts. Yes, it's slightly kind of an over segmentation, but just because the similarity value in here, or similarity values in here, were slightly different than the similarities values in there. But that's something that you can, for example, do with a clustering algorithm. Grouping similar regions in an image. But it's not restricted to images, for example. You can also use this for any other type of data. Images are very nice because we can visualize them very well. But in theory, there's nothing which prevents us to do this on any other type of data. So the goal is grouping similar things. Okay? So this is basically what I said. We want to group similar things, and what we typically have for those clusters is we have a representative for every cluster. This can be a region, this can be one single data point, this can be a reference intensity value, or a reference texture in an image. So the important thing is that most of the time in clustering, we represent this cluster with a single element or a single token. This can be, if we have 3D data points, it may be the center, the mean of all those data points in the 3D world. If these are regions in an image, this could be the mean intensity value, for example, in this region, maybe even combined with the pixel location or central pixel location. It depends on what we are actually clustering. If we are clustering in intensity values or clustering in pixel coordinates, this has an influence on how this kind of single element that represents this cluster actually looks like. Okay? Clustering is often used for simplifying or reducing the complexity of that data. So if you think of an image, we as humans are still pretty good in identifying or interpreting images because our brain and our visual system is actually trained to do that quite well. If we look to other data structures which are not 2D images, which are some 4, 5, 6-dimensional data points, it's actually much harder for us to do this. And clustering actually helps us to simplify the data, to basically summarize the data so that we can easily interpret this data. It still also holds for images that we can simplify data and do certain tasks, group it into regions which are relevant in order to kind of have it as a basis for image understanding. I still have another example like this one over here. This is a picture of a scene of a lake and some greens, and you can see there actually regions, similar regions are also grouped together. So we have kind of this beach or sand regions. There's some sand regions over here, something darkish looking over here. There's all the green grasses, the lake, sky, clouds. So we even have the area broken up into something which looks very natural to us. And if you look to this, it looks like there's a semantic meaning behind it. Let's say whatever, grass or lake. But actually, clustering doesn't have this semantic meaning. It's just based on the differences in intensity values. So all of them are green. There are some dark ones, some bluish ones, some other blue over here. That's the reason why they have been broken up, but not necessarily because there's a semantic label associated to this. And this is kind of an important difference between clustering and classification approaches, that we do not have this label here. And for clustering, we typically do not have training data at hand. We do not require training data, at least for most of the algorithms. The only thing that we, however, need to do is actually we have to specify what similar means. So is similarity defined in intensity values? What means similar? Are we considering intensity values from 0 to 255, or do we have more bits available? Then your distance function may look different. And so it's very important to be aware of what your distance function is and what, for example, thresholds or what similarity means in terms of this distance function. And this is basically the key design criterion that the user typically has to specify in order to give the algorithm an idea what is similar, what is close to each other, which data points are not close to each other. Okay, so the key challenges that we have in here is, if we simplify it even more, is what makes two data points, image regions, areas similar. So this is our similarity function. This is the first thing that we need to specify as a designer. And the second thing which is important is how can we actually group those pairwise similarities. So given we can, between all the data points, we can compute a pairwise similarity. That means we have a distance function of every data point to any other data point. It's still a little bit unclear on how we would actually group them together. So if we have two pairs, we say, okay, those two data points form a cluster. And then maybe another data point and the two data points I had before should be merged into a cluster. And how is a strategy for example, merging those pairwise similarities into clusters, or how does this grouping actually is going to happen? So these are kind of the two key challenges or design decisions that I have to make, and which has a big impact on how our clustering algorithm in the end will work. So at that point in time, it's kind of the overall concept clear what clustering means and what the key idea behind clustering is. Was there anything I can clarify at that point? Okay. Okay, so then we may ask ourselves why this is actually relevant for us. So what are key things that we may want to do with the clustering algorithm? The first thing is something that we call segmentation, and this is something which is very often used in images, but also in other domains, is actually want to separate regions, typically in an image, or can also be in a 3D point cloud, or other types of data structures, into different regions. So I want to say, there are certain things which are the same, they form a region or an area, and then there are other areas. So for example, if we take a picture of that scene looking out of the window over here, one cluster could be, for example, the building Nussali 17 over there, and then a second building could be the lecture hall building there on the left-hand side, and they would form potentially an individual cluster. although these are two buildings, so from a classification point of view, they would both belong to the same semantic class, we might want to break up them into two different entities because they're two different buildings. And maybe the vegetation here in front and the footpath here in front could also be own regions. And then a segmentation algorithm would actually break that up into those regions. So the example that we have seen before, these were actually, was this type of problem. We were basically segmenting our image into similar regions. Other things that are relevant is, where I said before, summarizing data. So if we have a large number of data points, we may want to simplify our data, reduce our data, and clustering algorithms can make their contribution to that, to basically simplify the variation in the data points that we have to a few representatives and then represent our data with these representative elements. They could also be, they're also used in combination with classification or learning approaches. For example, if I can group things which look similar, I can simplify my labeling effort and say I only need to label the representative of this cluster and then assign the same label to all the other clusters. That's something which is typically less accurate than doing, for example, pixel-wise classification in an image, but it allows me to actually have a consistency among those regions, and it's something which typically can be done much faster than classifying every individual pixel if I only have a small subset of pixels I need to consider. You could do things like these segments or these areas are sometimes also called superpixels. So basically you have a group of pixels which have the same meaning, but they span over a larger area. So you can see this as a form of superpixels. And then you only need to run your algorithms on those superpixels, on those kind of larger groups of pixels in order to simplify the efforts. And that's what clustering algorithms are actually used for, or also frequently used for. Okay, so these are some of the examples, let's say the most popular things that you can do with clustering. There are more things you can do, but these are kind of probably the most prominent ones. And the next thing is basically an outline of what happens in the lecture today. We look into basically three types of algorithms. The first algorithm is agglomerative clustering, which is a very easy and intuitive form of clustering, which works very natural and is one of the standard choices. Then we'll look into k-means clustering, which is, some of you probably have heard k-means already. It's basically you're taking your data points and you represent this data points with k representative elements, and those k representative elements are basically computed as the mean over the data points associated to these representatives. And there's an extension to this. You can say soft k-means, where this assignment is not a hard assignment, and this is something which is very similar to computing Gaussian mixture models with something like the EM algorithm. And I will very briefly at least illustrate how this Gaussian of mixtures can work out. And then as a last part of the lecture, I want to look into the mean shift algorithm, which is, or mean shift clustering, which is one of the popular algorithms that can efficiently be implemented and is often used in the image domain to actually generate those similar regions. So it's kind of the outline for today. Especially these here are algorithms that you will use in your life very, very likely, because at some point in time you will work with some type of data which requires grouping them, and k-means is one of the standard choices for this, probably the most frequently used clustering algorithm. And therefore, that's something that will pop up in your life again with very high likelihood, but all the others are two very frequently used techniques. Okay, let's start with the first one. And the nice thing about this one is that it's extremely easy to understand. And we can very easily go through it, and it's very intuitive on how it actually works. So consider we have, these is our distribution of data points in the 2D plane, and we want to group those data points now into similar regions. And what we assume to have is we have some distance function over those data points. So in this case, this would most likely be the Euclidean distance in the 2D world. And agglomerative clustering starts with says, okay, I start saying every point is its own cluster. So we have n data points, we start with n clusters. And then the key thing of the algorithm is to go and combine clusters which are most similar. And then basically merge those two most similar clusters into a new cluster. And then continue this process until I'm happy with the result. So if you think about all those data points over here, and every of those data points forms an own cluster, then the next thing is find the two closest clusters and merge them. So if you look to this data point, this is probably here. These two data points are the closest one. So the next step would probably be to combine those 2 points into one single cluster. That means basically I'm taking out these 2 points and representing them with one new point, at least from the conceptual point of view, and adding one data point representing those 2 data points back to the data set. And then I repeat the process. Which are the next 2 closest ones? And so on and so forth. In the end, I can merge this up to one cluster if I take it to the extreme, which would represent the whole data set. Okay, so let's see how that works. So the next thing is find the 2 most similar pairs of clusters. And in this case, this is kind of this blue illustration here. Those two elements will be merged into one element. And I can use, what I can do is internally, I can actually build up a tree by saying, okay, these are my 2 data points, which are those 2 stored with an ID, and I can merge them on a higher level, basically with a tree-like structure, into a new cluster, and this cluster represents those 2 elements. You can also envision this as being multiple of data points being here, which are just not shown, the individual ones. Okay, so this results, I merge these 2 guys here into one area, and this is exactly this area over here. Merge them as one cluster, and then I basically repeat the process. Now we have this blue area, which is one cluster, and we compare all other pairs with each other. So I may find another one which sits somewhere over here. Maybe this data point is the closest one. So I merge these 2 elements into one cluster. I create a new green tree for this, and then I continue this process over and over and over again. So the next thing may be, for example, this point over here now is closest to the blue cluster over there. So I may want to merge this black point with this blue cluster. This is already an existing cluster which has more than one point in there, and I'm adding a new cluster to it. So I merge them, so now I will have a group of 3 points involved. So if I illustrate this as a tree, I'm basically assigning the red element to the blue cluster. So I have the blue cluster and the red element, and this forms now this red cluster over here. So you can see that I start actually getting up a hierarchy of those trees. Or not a hierarchy of those trees, this is still a tree, but I now have an additional level on my tree. So I'm basically building up the tree from the leaves toward the root. It's different to most other algorithms that we use when we construct trees, where we typically start with the root node and grow from the root node. Here it's basically the other way around. I start from the leaves and basically grow individual trees, which are then merged one after the other. And I basically continue this process until all of those elements are merged into one single cluster. So we'll get a lot of those small trees, different trees are merged. In the end, all those individual trees will be merged so that one tree structure actually evolves. And the lower I am in this tree, so the closer I'm to the leaves, actually the shorter the distances are between those 2 elements. And the higher I go in this tree, the larger the distances between the merged clusters, because I'm doing this iteratively, building this up. So the question is, what's the similarity function? And in this case, we said, let's say it's a Euclidean distance between 2 data points. And the second design decision I need to make here is, how actually is this distance computed? If it's computed between 2 individual black elements, then it's actually quite easy, because it's just the Euclidean distance between those 2 points. But what happens in exactly this example, where I want to compute the distance between the red data point and the blue cluster? What would be a way to do that? Any proposals from your side? How would you compute the distance between the red data point and this blue cluster?
There could be like a mean point, or it could be one of, for example, in this case, of 2.
Yeah. So one idea would be I could represent these 2 blue points by a new point, which is given by the mean of those 2 blue points. And then I compute the distance between the mean and the red point. That's one option. The other option is I take, as you said, the closest point. So I take the point among the blue points, which is closest to the red point. What other options do I have? So we're going to go for the minimum point. Yes, exactly. The furthest, the one farthest away, is the maximum distance point. That depends on what you want to do, what the clustering is in the end used for. So if you want to ensure that within a cluster there's no distance between 2 points larger than something, it's a very good idea to merge them based on the maximum distance. If you want to ensure that 2 points within a cluster can be reached, and it never is, there's always a neighbor which is closer than a certain distance, then the minimum distance would be the right way to do. Or if you are saying you're interested in average distance, then the mean would be the right point. So the question is how you actually compute this similarity between which elements. So again, if you have 3 clusters over here, you want to compute what the distance of this triangle to the these different data points. If it is, let's say, the closest one to the blue one, this would be the closest distance. This would be the furthest distance, and this to here would probably be the mean distance. And the same holds for the red data points as well. Okay? So this is again a user-designed choice what you have to do. And what one also sometimes distinguishes the difference between using the mean and using the min or the maximum distant point is that if I compute the mean, I'm basically computing a new element, a representative which is not part of the original data points. There's nothing bad about it, but this is something I need to be aware of. So if I represent these 2 data points with the mean data point will be sitting somewhere here. It is not a member of the original data set. Depending on your application, you may not want to introduce those new points. You want to just stick with existing data points. So in this case, it means you need to select one of those blue points as the data points you want to represent for. This would be the minimum or the maximum strategy, for example. Okay, so if we continue this process, we will actually get up a tree which looks like this. So this is an example. These are the IDs of all the data points, and you can see how they are individually merged. So the lower I am in the levels of my tree, the closer the distance. And you can actually draw the distance over here. So what you see here on the x-axis are basically the data points, the IDs of the data points that we have. And what you see here is the distance between data points or between clusters. And so if I then pass this tree from the bottom upwards, whenever I see the 2 data points are connected, they are connected at that distance. So data point 1 and data point 2 probably have a distance here of something like 0.15. And these 2 clusters over here have a distance of approximately 0.5. And then if you build up once this tree, or this tree-like structure, also called dendrogram, then you can actually go through this diagram and basically select your cutoff threshold where you want to say now 2 elements are not similar anymore. So you say, okay, I assume my maximum distance is whatever, 0.45. So if things are closer than 0.45, I don't want to merge them. This would be equivalent, not equivalent, this means you're actually making a cut here and cut the clusters off into 1, 2, 3, 4, 5 different clusters. If you, on the other hand, select my cutoff distance is 0.6, then you would have 1, 2, 3, 4 different clusters. If you decide your cutoff distance is 0.8, you would have 1, 2 clusters. And if you say 1, you would have a single cluster. So what is nice about this algorithm, you can basically, once you've built up this dendrogram, you can actually path through this dendrogram and select cutoff thresholds and basically break things up into different clusters in a quite easy and intuitive way. Or you can go the other way and can say, okay, I want to have 5 different clusters. Then you basically start from here and go down the tree until you basically pass down the threshold until you reach 5, which would be somewhere over here. So if those are identical, that's, no, actually here's a 5, cutoff distance of 5. Here, sorry, like this. So you can basically pass down this diagram and see until you reach 5 clusters. And then you say, okay, now I want to have 7. You just lower it until you reach 7. It's not guaranteed that you will get exactly 7. Sometimes you have 6 or 8 because 2 are on the same cutoff threshold. But you can very easily path through this diagram and actually select the number of clusters or can select the minimum distance that you actually want to generate. Okay, so that's all that is about this algorithm. It's a very simple algorithm which allows you in a very easy and intuitive way to actually combine those clusters. It's very simple, also rather simple to implement. You just need to compute distances between those clusters, and it depends a little bit how you can implement this efficiently. If you need to add new data points with the means, or if you stick with the data points that you have, then you can use things like KD trees or other data structures to make things even more efficiently. But otherwise you just need to compute distances between data points. And you are not restricted to certain types of shape that those clusters may have. And based on using the threshold, you can actually make certain design decisions. So you don't need to commit initially on how many clusters you want to have. You can first build your diagram, and then just by changing your threshold, add or remove clusters by merging or splitting up individual ones. So in the end, this provides you a hierarchy of clusters, and you can actually pass through this hierarchy of clusters, which is something which is a rather elegant way. It, however, also has its disadvantages. Depending in which order those data points are processed, you may get imbalanced clusters. So some regions may grow very, very large. You basically get disbalanced trees that you have. And it's just the way how the data points are set, especially if you have regular structures. So with regular distances between those data points, it strongly depends in which order the points are actually processed. It impacts the result. You will get substantially different results. Again, you still need to choose your number of clusters or the threshold, but at least one thing you need to do. The question is, this can be a disadvantage, but it can also be seen as an advantage that you can select. You need to only select one of those twos, but it can allow you to actually generate very good clusters and very good clustering results, which are also intuitive for you to understand. But if your distance metric or your function is not as easy to grasp as the Euclidean distance we had in this example, things can get much more complicated. So if you want to group similar image regions, for example, and you're thinking in the area of intensity values, it may still work. If you look some measures of texture or something like this, then it's very much harder to find those distances, and the results may not be as intuitive as it actually looked like here. So it depends a little bit on the space that you're performing your clustering in. Okay, are there any questions about this first type of clustering algorithm? Anything I can clarify at that point? Okay, then let's dive into the next class of algorithms, which is the k-mean clustering. So again, k-means is one of the standard approach in clustering, and basically the idea is that you say you have a large number of data points, and you are basically representing a number of data points with something which is called a centroid, which is basically the mean computed of the data points associated to this cluster. So if you have say a certain number of data points like those over here, what k means basically says is, or requires you fix a number of clusters before. You say, I want to have 3 clusters. Give me the clustering with 3 clusters out of this, or with 5 clusters. And this is k, that's what it's called, k means. And then, let's say in this case we choose k equals to 3 in my example. Then one of the results would be that this is one cluster, and this is the centroid. It's the mean of those data points associated to this. This could be one cluster with the mean sitting here, and this could be one cluster with the mean sitting over there. So in these points here, those red points are those centroids. Or these are the means of the white crosses. Okay? So and the goal is to actually find this partitioning of the data into k clusters. This partitioning are those circles that I have over here. Or I illustrated them now with those circles. What you in practice actually get, you're basically breaking up your space into regions, and so you would in the end get a region which somehow would look like this. And these are basically the decision boundaries, those blue lines. So everything which falls into this region will be assigned to this cluster, everything which falls into this region will be assigned to this cluster, and everything which falls into this region will be assigned to this cluster. Okay, so this is the partitioning of the data that we actually get. And what we still need to do, we still need to define a distance function, and again, the standard choice for those distance functions is just the Euclidean distance in the space that I'm considering. So here in my illustration, this was a two-dimensional space, just because my blackboard is two-dimensional structure, but it could also be three-dimensional. So some of those points could stick out of the blackboard, or it could be a four-dimensional space, 5, 6, 7, 8, 100, 200,000. That in the end doesn't matter. It may have an impact on how fast you can compute your results, but it has no impact on the algorithm itself. Okay? Any questions about the objective that we're trying to address at that point of the k-means algorithm? So I haven't talked about how it works, but the question is the goal clear that we want to reach? Okay. So the goal then, my input is this k equals 3, and I want to get those centroids out of it, and maybe an assignment of all the points to the centroids. Okay? Okay, let's see how this works as, let's say, informally described. Not as an algorithm, we'll come to the algorithm in a minute, but let's try to informally describe how that works. So it's an iterative procedure, so there's a repeat until convergence in over here, so this thing is repeated over and over again. The first thing what I do, I just start with a random initialization of these here shown final result of red crosses. So I just say, I know I want to have 3 because that's the input to my algorithm. And let's randomly choose 3 elements and randomly choose those centroids. And what most approaches do, they just randomly select data points, 3 data points from the white crosses, and say, you're a centroid, you're a centroid, you're a centroid. That's it. That's my initialization. So a possible initialization, okay, found some green chalk over here, could be whatever, this one, and this one. This is one possible initialization. In this case, of course, this result is different from the final result that I have, but this is just my initialization. But it could be any other arbitrary points. Maybe also, whatever, this one, and this one would be another initialization. I'm not arguing which one is better or worse, but these are possible initializations. And the standard choice for k-means, if you don't know, if you don't have any other knowledge, just draw them randomly. Okay. So, and then we come to our loop. And what the loop does, it basically says, okay, we are now iterating over every data point in my data set, so all the white points, and I'm assigning the white point to the cluster which is closest to it. Okay, so let's start with my original initialization. So this thing over here, and now we can make an assignment and assign every of the data points that we have to the closest centroid. So in this case, this would be an assignment, and this would be an assignment, and here it probably would look like, maybe like this. Okay? So making assignment, which data point is assigned to which centroid. This was this step over here. Assign each data point to the closest centroid. That's what I've done here, drawn with my white lines. And then, once I've done this, the next step is recompute those centroid locations based on all the data points assigned to them. So basically saying, okay, this guy over here is not a very good representative for those 3 elements over here. Let's recompute them. And it's recomputed as the mean of all the assigned data points. So I'm basically computing the mean of this point, and this point itself. And this will, in this case, already lead me to the red cross over here, because this red cross is the mean of these 3 data points. So this thing basically moves over here. This is the update that I'm doing. Over here, I have, for this cluster, I have this data point, 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 this data point. So the result should be sitting somewhere probably here. Somewhere over here. So this guy moves in this direction. Let's try a circle so it's easier to distinguish them. And here we have 1, 2, 3 data points, so this one will be sitting over here. Or this cluster moves in this direction. Okay? Now, I'm going back in my repeat loop and then do the same job again. Assign all the data points to their closest centroid. Okay, so here we still have our 3 data points which are assigned here. And now here, something interesting happens. Now, this data point, which was originally assigned to this cluster, and has moved over here, now this one moved closer. So this one will be assigned here, this will be here, this will be here. This one is now moved further away, so now this one will be the closer one. And those will always assign to this one. Okay. And then I say, okay, adjust the centroids by computing the mean of the associated data points. Here, nothing changes. No assignment has been changed, so the point will not change. Here, this point, we only have these 3 points associated. This one will move over here. And in this example, all the points will actually move over here, which is now the final result that we have for our k-means algorithm. Then we go back, make an assignment again. And if we then realize nothing had changed in the assignment, the means will not change anymore. And then this is an indication that the algorithm is converged. If no assignment has been changed, the centroid locations will not change, and I'm basically done. I'm aborting the algorithm, and I got the 3 centroid locations which I started. Okay? So is the idea of the k-means algorithm clear? How it works? Can you intuitively describe how k-means works? Okay, so it's a random initialization in the easiest form, and then a repetition of 2 steps. Make an assignment which is the closest centroid for every data point, and then recompute the centroid by computing a mean. And then I'm iterating it. And then you also realize where the name comes from, k-means, because I put in the number k, because one of k clusters, and I'm basically iteratively computing the means of the associated data points until nothing changes anymore. Okay, so getting slightly more mathematical, how can we formulate this? So what we want to have k reference vectors or centroids, and they have here the index mi, so from 1 to k, and this, I want to find those which best explains my data point x, my data x. And I'm assigning all my data points called xt, so I have t data points, so that the distance between the data point and all possible centroids is minimized, an arcmin. So I'm basically choosing the index I so that the distance of the data point to a centroid is minimum. And this exactly means nothing else than assigning to every xt an index which tells me centroid number 1, centroid number 2, or centroid number 3. Okay? So this arcmin basically says the first thing, assign to every data point the closest centroid. This is the same statement expressed as a formula. Okay, and then I can also formulate this kind of as an optimization problem, which has the following objective function, R, which is sum over all data points, T, sum over all centroids, and then have an index variable B, to which I come in a second, and compute the Euclidean distance between the data point and the centroid. So if you don't take this BT into account, or if the BT would be always 1, this would mean you're summing all distances of the data points to all centroids. But the elegance comes from this indicator, this Boolean variable bt, which is always 0 except for one index it is 1. It's for the index where this argmax actually holds that we were just mentioning. So bt is 1, that means there the distance is activated if it is the closest cluster, or it's 0 for all other clusters. And if it's 0, this function is basically not considered, the distance is ignored, and if it's the closest one, the distance is used. So by using this indicator variable, b, I can basically formulate this as a nice function over two sums, but it only sums up the distance if it is the closest data point. And then the overall goal is to minimize this function. And the results of those three centroids in this example is the result that actually minimizes this objective function. And once I've done this assignment, I have my objective function. I basically can use the same notation to recompute the means by saying a new mean for the centroid I is take all data points, take only those which are the closest one, the others are set to 0, they don't count, compute the sum of the data points, and sum up by basically the number of assignments of assigned data points. So this is nothing else than a mean computation. This computes the mean location of mi, giving the data points xt that are associated to the index I. And this is exactly these movements, which are here had indicated by those red arrows, the movement of my centroids. So then as a next step, I can put this actually into an algorithm. And this is the algorithm of that form. I say, okay, go iterate over, or you first do an initialization, randomly select k clusters from my data points. And then I repeat for all data points. I compute this indicator variable by iterating over all my, or finding the minimum distance. And then recompute the mean based on this indicator variable and repeat this until I converge. Still, this question is what does convergence mean? It's something which is not necessarily super trivial to specify, especially if you have a large number of data points and you can run into numerical issues that based on rounding points may jump in their assignment. But at least from a mathematical point of view, the thing is as soon as the assignment doesn't change anymore, you're sure you're done. Typically, in practice, if you implement this, then you often stop the iterations of the k-means if the distance in the assignment doesn't change anymore. Because it can be that the cluster is exactly between, a point is directly between two centroids, and it's basically jumping forth and back all the time based on numerical instabilities. Something that can happen, especially if you use approximate or approximate distance functions in order to have fast calculations. So this can be a little bit of a long debugging session if you don't know about this and you just realize your algorithm doesn't converge. But at least if you write it down on paper, we're sure we can stop if the assignment doesn't change anymore. The other alternative we can do is we basically monitor all the centroid locations, and if the centroid locations change only epsilon, we say we are done. Okay, let's have an example. We start over here. This is the green points are our data points, and the red and the blue one are, for example, initializations. In this example, there haven't been data points from the data set. You can also choose another one. Typically one does, but in this example, for visualization purposes, this has not been made. Okay, so in the first step, we make the assignment of every data point. We basically color those data points. Blue means they belong to the blue centroid. Red means they belong to the red centroid. And this is basically the partition function. So what I try to draw here with these blue lines. So whatever lies right of that line is red. Whatever lies left of that line is actually blue. So I made this assignment. Now I need to recompute the red and the blue cross as the mean of the blue points and the mean of the red points. So this one will actually move down here, and this one will actually move up here. So you can see this. Here's now our red cross, there's our blue cross. And then I do the same thing again. I restart again, next iteration. I make the assignment. Everything which is close to the blue one gets blue. Everything which is closer to the red one gets red. So my partition of the space now looks like this. Then I recompute the mean, so this one will move down here, and this one will move a little bit up here, so that I get this result. Again, compute my separating function, recompute the mean, recompute the function. You can see already the separating line doesn't change a lot. The only point which has changed is actually this data point over here, which here was blue, here it's red. Now recompute the result, and now the association that will not change anymore. And from this point in time on, there's no changes in the data, and everything is constant. And we converged, and the clusters do not change anymore. Okay? And that's all that there is about k-means. The only thing you need to be able to do is you need to be able to compute distances, you need to be able to compute a minimum, you need to be able to compute a mean, and implement a loop. All things which should be doable. Again, in practice, the initialization has an impact on how good your algorithm works, because it depends on the initialization. You're not guaranteed to get always the same result. The algorithm will converge, but it may converge to a local optimum, not to the global optimum. And the second thing is the convergence criteria needs to be defined, and numerically this can be a little bit tricky. And what in practice can be an issue is computing all those distances, because in the end you need to compute the distance of every data point to every centroid. And this is something which can be a computationally costly operation. And there are ways or algorithms to speed that up, to be more effective in computing these distances. So one data structure that most of you probably know is the KD tree, which is a logarithmic data structure where you can search in logarithmic time for neighbors. And this is one approach you can do. But there are even better approaches for finding close nearest neighbors, which do not generate or do not guarantee to provide exact results, but are approximative. So you may have small errors in there. You won't get exact distances out there, but which are orders of magnitudes faster than a KD, or not orders, but substantially faster than a KD tree. And these are often used in practice. So there are some tweaks and knobs you can turn if you turn this into practical algorithms, but this is basically the basic concept behind it is actually very simple. So k-means is also similar to agglomerative clustering, actually quite easy to implement and easy to understand. You can actually quite well debug what's going on just by visualizing your data points. You can actually really see and understand what's going on. It's also rather efficient. So it depends on the number of iterations, and every iterations I need to iterate over all cluster and all data points. So n times k times t. You may argue, that's actually not the most efficient way. That's true. You can do this in a more efficient way, for example, using KD trees or approximative algorithms, so which are not exact anymore, give you the exact distances, but an approximation of the distance, and then you're even faster than this. So this is basically the naive implementation that we have illustrated over here, which has this performance. You can get even better. The algorithm converges. The important thing is only it's guaranteed to converge, but it's only local optimum. It's not necessarily a global optimum. And even the guarantee of convergence is kind of assuming there are no rounding errors, no numerical errors. So in practice, you may run into numerical issues. But still, it's a very simple algorithm. It's excessively used, and from my point of view, the most popular clustering algorithm that is actually out there. So one of the things where you can actually use it for, if you have an image and you want to compress the image by reducing the color values, the intensity values that you want to use. So consider you have a grayscale image with 256 different grayscale values, and you want to reduce them to 8 grayscale values to reduce the complexity of the image and save storage, for example. One thing you could do, you can equally space your intensity values that you're using by dividing 256 by 8. This gives you a spacing of intensity values. Or you can actually run the k-means algorithm on the intensity values, and then it will actually try to find those intensity values which best represent your data to minimize the difference between the compressed image and the original image. So using the k-means algorithm for doing this is much better than taking a uniform spacing of possible intensity values in your image. It's kind of one example where you can actually use it for example, for reducing the color depth of an image. So what is suboptimal in k-means? First, you need to specify k. Maybe you have no idea how many clusters are in your data, and you would like the algorithm to figure it out. That's something that k-means can't provide. You have to provide how many clusters you want to have. Although I have to say you can make some assumptions about your data, and then there are algorithms for actually estimating how many k's, how large k should be. You can define an objective function, but then you basically need to run k-means multiple times and vary it a little bit to see if you actually get good results and if it satisfies your needs. But this requires you typically to know something about your data or make some assumptions about the distribution of the data points that you had at your input, as your input. The second big disadvantage is that the result depends on your initialization. So if you run k-means multiple times, you have a random initialization, you may get different results because it's a local optimization algorithm. So the initial guess matters. Similar to your nonlinear least squares, your initialization matters. Your initial guess is important. So you need to find ways for actually initializing this algorithm well. This becomes especially important if you have outliers in your data. Let's say if some data points, a small number, which is completely off and they're extremely far away. If this happens, and especially one of those outliers is picked as initial centroid, then this centroid location will not help because just the outliers, it basically put the outliers in the centroids, which is not what you want. And even if this is not the case, even if you don't initialize your centroid there, you have one data point which is very far away, it will actually drag the mean quite substantially far away. So you get suboptimal estimates for your centroids. So k-means is sensitive to outliers, and you need to have approaches that you need to have algorithms, or you need to have techniques to identify outliers or clean your data from outliers. Otherwise, the results will be suboptimal of your algorithm. So if you have outliers in your data or afraid of having outliers in your data, k-means may not be the best choice. Okay, so basically to sum that up, it's a frequently used algorithm, it's easy to implement, you need to choose k, it's sensitive to outliers, something to be aware of. You will only find local minima, and there is, but still it's very simple because you don't need to do anything more than computing distances and means. In image-based clustering applications of grouping similar regions, it's not that often used. There are other algorithms like the mean shift algorithms, which we introduce later, which are more popular because they typically give me better results for the image domain. You can nicely combine intensity values and distance values, so they are more frequently used. But for data, you have no other idea what's going on in here. K-means is typically the first thing that you try out and see how well your clustering results are. Okay? Okay, with this, I will make a 5-minute break, and then we are going to continue with the remaining part. Okay, so after having introduced the k-means algorithm, I want to now look into the mean shift, which is one of the popular techniques for image-based segmentation. And this is actually the algorithm which provided also the data for the initial example with the grass and the lake. And these are different examples that you typically get out of the mean shift algorithm. So you actually can realize that you get actually clustering or segmentations that are not one-to-one associated with semantics, but it's actually not too far away from a semantics. Although the algorithm has no explicit or implicit mean to have a label or something. It's just really based on difference in appearance. And in this example, the appearance is done based on color space, so based on color, so the intensity value, and also the location can play a role. So you can actually combine intensity value or color values and pixel locations if you want to do this. So things which are closer in the image spatially are more likely to belong together, and at the same time, elements which are closer in color space are closer to each other. And what the approach does, it basically tries to approximate the data points by a density function, and by a non-parametric density function. So we're not restricting ourselves to Gaussian distributions, but we are making a non-parametric estimation. Non-parametric means we don't have a closed form which describes us, but we use the data points itself or a kernel on the data points itself in order to represent this density function. And again, the dimensionality you're looking into can be just the intensity values, but can also be a higher dimensional input space consisting of intensity values and pixel locations, for example. So what ended happens, we're taking an image like this one and mapping it to some other space. This can be just the color space, taking whatever RGB values, or typically one uses another different color space, but it may also take into account the data points in the pixel locations of the data points. And then you get a data point description like this. Then you're estimating a density function, basically a function which says the higher the density of those points in here, the higher the function value. Then you can get something which may look like this. So based on the blue is low, red is high, and you can see look like mountains, where and the higher the mountains, or the higher the function there, the higher the density. And what then the k-means algorithm does, it tries to find the peaks in this density function. And all the points which lead me, if I make a gradient, follow the gradient, leads to the same peak, or the same maximum value, those are considered to be clusters and are grouped together. So let's investigate this with a little bit more with an example how that actually looks like. So the goal is the points represent a density function, and we want to find the maxima of those density functions. And all points which are close to those maxima, they are regarded as belonging to that cluster. Or basically those which are in the, let's call it basin of attraction. So which if you follow a gradient will lead you actually to the same maximum. You can see this consider this like mountains, and if you just always walk uphill, you will reach the top of individual mountains or individual hills. And every hill is an own cluster. And so if you have, let's say, thousands of people, let them start in random places in the mountains and let them everyone gets the command, just hike upwards. And everyone hikes upwards until they reach the mountain, and then you can see different people ending up at different mountains, and you assign the points where they started to the mountains where they ended up. And this is the clustering that this algorithm actually generates. Okay, so let's try with an example. So this is the data points in the 2D space that we have. And let's say here we start with a data point in this area. Say we want to now compute for this point to which cluster does it actually belong to. Then what the algorithm does, it takes into account a region of interest, basically like the local neighborhood. You can see this if you think about these mountains. It's kind of where do you look for your gradients in your local neighborhood? How large is this neighborhood that you're taking into account also for smoothing out, let's say, very small deviations in density. Okay, so for every point you have a region of interest, and for this region of interest, you now want to compute a density function. So what's the density of points in this region over here? And so the next question is, how can we estimate this density, a density function for those points in an appropriate way? So again, what we want to take into account points which are in this region, and how can we say there is a small number of points here and a large number of points here? So what is a way for representing this in a non-parametric way? That means not representing it with one Gaussian distribution with one mean and one covariance matrix. What are ways for actually doing this in a non-parametric way so that we take these original data points into account? Any ideas what we could do? Standard approach to non-parametric density estimation. Sorry?
Assigning weights to the point.
How would that look like? Make a proposal. You're going in the right direction probably, but from the way you answered the question, it's probably very hard for your colleague students to infer what you mean. So can you be a bit more precise and elaborate your ideas a bit in more detail?
So depending upon the distance from the mean, each point will be given a weight.
Yeah.
So
So I mean, for this point, you take the weighted mean of all the neighbors. Okay. How do we compute that weight? Any ideas how that weight could look like?
Weight would be the distance.
Okay, so you would take just the raw distance into account. Okay. Any other proposals? We're coming closer. Any other ideas? So the idea was actually not too bad. Actually close to what you do, except that you don't take the Euclidean distance into account. So what we typically do is we take a point. For every point, we look into the neighborhood and collect all the other points which are there, which are here, these red points. And then we say, what's the distance of those red points to the point I'm actually interested in? And then I put this into something that's called a kernel function. So through another function, which, for example, can be a Gaussian distribution or an exponentially decaying function. So you can also see this differently, that you put a Gaussian over every individual point, and then at every point in space, you basically have some of these Gaussians you're taking into account. Okay? So this is something which you typically do with the kernel function k. So you can be writing my function f of x that I'm representing, my density function, is the sum over the points in the neighborhood, m. And then I say this is the kernel function k, which takes into account the distance from the point that I'm considering and the neighboring points, those red points in this example. So this would be our query location, and this would be the neighboring points. And in practice, this is typically something which depends on the squared distance, normalized through something of variance, and is an exponential function in most situations. So like the Gaussian kernel is the standard choice that we are considering. So basically, using a Gaussian kernel, and you're smoothing out those individual points. Actually very similar to the convolution of images if you think about this. So if you think about back in your bachelor studies, photogrammetry 1 course, where you see those red dots as, let's say, the black pixels, and everything else is white space, and then you perform a Gaussian smoothing over this space. It's actually a Gaussian convolution. It's actually very similar to what's actually going on here. Okay, so what we can do, again going to our example, we have our region of interest. We can compute the center of mass for all those data points. And then we say, okay, just follow in the direction of the center of mass, because there the density is expected to be larger. And then this gives me a shift vector and shifts the mean towards the new location of the mean in this area of interest. So this actually, and what I'm doing, and from the algorithm, I shift my data points towards the mean. This can be seen as saying the example in the main example of the mountains, that I'm actually, these are a few steps uphill. So I look to my local region and say, where is it going upwards? And then I'm walking this direction. Because the criterion is, where is the density of points increasing? And then I basically repeat this process. I say, okay, compute the new mean from the data points in my region of interest. And then, again, compute my mean shift vector and move the mean shift into this direction. And again, repeat this process and continue. What you can see is here in this example, we are actually ended up in this example in the region which has the highest density of points. Because now the mean shift and my current location, the new location and the original location are basically in the same place, or very close to the same place. So I reached kind of a peak of one of those mountains. So and the mean shift vector is computed in this area by taking exactly my kernel function into account. So all the points times the kernel function, normalizing it through the kernel function. This exactly gives me this kind of weighted mean that I'm computing over these data points, and the weight is actually the result of this kernel function, which is in most of the cases an exponentially decaying function similar to a Gaussian of those data points. So I use a Gaussian kernel and compute the mean of this Gaussian kernel, and then this is my mean shift vector by subtracting the original location so that I exactly have this shifting vector. And I'm basically shifting my data points all the time. So this is this point, this is the shift vector, the new point, and then this is basically my shift vector. And this is where the name comes from. You're basically shifting the mean towards maximizing it. And the mean here is representing the density of the points. So you're shifting your position so that you're maximizing the density of points in your local neighborhood. And this leads you to peaks, to dense regions. So and if you think of this, let's say we have this distribution of data points with these red crosses over here, you can basically start at every of these individual locations, at every data point, and perform the mean shift. And then the mean shift will guide you into different locations. So if you start here in this area, you will end up at this peak. If you're starting here in this area, you will actually end up in this peak. That's by trying different starting locations. In my analogy before, these were the people you set up in the mountains for start hiking. These are the individual data points that go uphill all the time. And these are then the two summits where those people will end up. And so if you have, again, our examples here, these are our data points from the initial example. Then you can even encode it here with those color spaces. And then you can see here all the points which start here will actually run through those peaks. So the peaks or the summits are basically those red points over here. And whoever starts here will actually end up here at this point. So these are all those yellowish values. These turn out to be all the blue values over here, and so on and so forth. So what the mean shift in terms of an algorithm does, it seeks to find the modes of the density function given the set of input points. It still depends, you still need to decide what's the dimensionality of your input points. Is this the intensity values? Are these color values? Is this some special color space? Does this take color and location in the image into account? This is basically defines what your input space is. What you then need to do, you need to choose your kernel function. Standard choice is a Gaussian distribution. And you have your variance of your Gaussian, your h. And this tells you something about the distance, so how spread are those points. So in terms of intensity values, is basically tells you how close are 2 points if they have a difference in intensity values, let's say of 100 intensity values. Is this close? Is this very far away? To which weight should this be matched? Should it be something close to 0 because they have nothing to do with each other, or should this be a high value because they actually have something in mind? Basically gives you scaling in that space you're considering. And then for every point, you basically run this algorithm. You center a window around this point. This was this illustration that I had, that circle. You compute the mean of the data in that search window, take into account the kernel, the weight, and then you center the search at the new mean location that you compute in this circle. And then you repeat the steps B and C until you converged. And once you converged, you assign the data point that you determined in A, the final location that you get after convergence. And then, at the result, if you do this for all the data points, you look where do they end up with, and this represents the resulting cluster location. Okay? So it's kind of the idea clear of what we were doing. Yeah?
So how do you know in this algorithm that you found all the peaks, all the modes, if you initialize randomly, right?
No, we're not initializing randomly. We iterate, what we're doing, we're iterating over every point. Every input data point is considered. So we start every data point, compute the neighborhood, and then run the mean shift, and we'll end up at a certain point. Say, okay, for data point number 1, we end up at this location. For data point 2, we end up at this location. Data point 3 ends up there.
So if you choose randomly the region of interest, so it could happen, right, that the region is so small that you don't end up.
Yes. This basically defines this bandwidth parameter. So this is basically the design or the choice of the bandwidth parameter in your kernel function. If you set this too small, you basically only the individual point matters, and every density is like it's like a sum of Dirac functions in the most extreme case. So every data point will be its own cluster. That would be the result. So then every data point, if you think about the space of intensity values, it would mean every intensity value would be one cluster. So all red pixels are one cluster, so all green pixels are one cluster, all black pixels are one cluster. This is the extreme case. And now if you increase your value of h, it turns these Dirac distributions into Gaussian distributions, and then the neighborhood starts to matter. So in the end, you're right. The choice of this bandwidth parameter, h, tells you basically how many clusters you get. If you make it extremely large, it's just the mean of everything. You take all data points into account, compute the mean, everything is one cluster. This is the other extreme. So you also have one parameter similar to this agglomerative clustering in the end, where you merge them where you are, and this is your kernel parameter h.
The other question is that you showed like a kernel function,
Yeah.
and you wrote like norm and square.
Yeah.
Meant L2 norm or?
Typically, yes.
Norm?
Typically, it's
Okay.
L2 norm. So typically, what it
K-means you wrote like a norm, and so I was like confused.
yeah, okay. In the end, because this comes from because this is typically the element, the square that you have in the Gaussian distribution, and then if you take a Gaussian kernel, the h would be the variance, and this is your expression. You put basically a minus exponential function in front of it. That's where it actually comes from, because then your function k would be x of minus x. So the thing which is important, or what you want to do here, is the kernel function should only depend on the distance between the data point you're querying and your neighboring data points. It shouldn't depend on the actual value. So the kernel function should not be different because it's here rather than the kernel which is here. So it should not depend on the place where in the image. Therefore, you typically phrase it in a way that you say it depends on the distance between the data point and the query location that you have, and express it. And the square, I can also leave out the square, and then put the input into an exponential function, square the exponential function, then h would be the standard deviation, not the variance, but it's basically equivalent. Just the way how you and the thing is, you don't have to use a Gaussian kernel. It's a standard choice, but you could also use, if you know your data points have some other properties, you may use a different kernel function. You can also use the different kernel functions for different dimensions, something I will come in on the next slide, because if some of your dimensions are intensity values and some of your dimensions are distances in the image space, you may want to use different parameters to quantify what means close in pixel location and what means close in intensity values, and you will have a different kernel function for this.
So in higher dimensional spaces, even the units are not.
Of course, it depends on what your space looks like. So if you have, even in two-dimensional space, if one location is a spatial distance and the other one is an intensity value, they're hard to compare. Just taking the standard Euclidean distance may not be the right choice. If one dimension is scaled from 0 to 1 and the other one from 0 to 1 million, then the one from 0 to 1 million will always dominate the distance. So you need to normalize this or use different bandwidth parameter for the individual dimensions. Okay, any further questions at that point? Okay, so if you actually implement this, the key thing in this is actually something you were referring to. You need to compute your features or your data point for every pixel. So you need to turn every pixel into a data point. This could be the color value, just the intensity value. This could be some gradient information you may want to take into account. This could be texture. This could be the pixel location. And in the end, what you typically have, you need to set your kernel size for the feature descriptor and for the position. So in this example, for example, color and position in the image. And they have two different kernels. They're typically the same kernel function, the Gaussian, but you use different bandwidth parameters because a difference of 3 in pixels means something else than a difference of 3 in intensity values. And then you initialize your window at every pixel. So if you have 1 million pixels, you need to have a million starting points you start up with. And then you perform the k-means, the convergence. And then what you typically also need to do is if you run your algorithm and you abort your convergence at some point in time, depending on your numeric quantities, depending how dense the points are, there may be points which are extremely close together at the final location, and you want to merge maybe points which just differ in a few sub-pixel differences or locations. So you may want to merge peaks which are very, very close together. But if you do this, you actually get very convincing results. So if you think this is your original input image, And just without having any knowledge about any semantics, just using the color information and distance information, you can actually turn this into a segmentation which looks like this. Which is actually pretty, from my point of view, when I saw this for the first time, I found this pretty astonishing that you can actually achieve these type of results. Also here in the mountains, in this mountain view, very easily get the mountains separated from snow areas, even from green areas, and from the sky. So you get actually pretty good results from those segmentation algorithms. Of course, it requires you to set your bandwidth parameter in the right way. So if you completely change your image and you remove the contrast dramatically, of course, or increase your contrast dramatically artificially, then of course you may need to change your H parameter over here. Some other examples also I showed before, and also the example that I had here in the initial results. You see here, and even under this URL, you can actually see other results or further results that you actually can obtain, how you can obtain those results with this mean shift algorithm. And today, the mean shift is one of the standard algorithms used especially for image-based segmentation. If you want to segment your image, it's one of the standard choices you actually start with. So if you look again to the advantages and disadvantages of this algorithm, so it's a pretty good general practice segmentation algorithm which segments into similar regions, and it became very popular in the image domain. Another advantage is actually rather robust with respect to outliers. You typically later on, if you, let's say, have outlier points which are extremely far away, they are very individual peaks with a very small basin of convergence. You can very easily eliminate them later on by simply see how many of your pixels or your data points actually ended up in there. This, of course, you can also do with other algorithms, but it's not as in k-means where you have the pure distance and the mean which is recomputed all the time, which would drag your clusters extremely far away from other data points. So this works better in the presence of outliers that you have in here. Disadvantage, you have to choose your kernel size. And this is probably something which is not very intuitive, or which you cannot do easily by looking to an image, say, of course, I need a kernel size of 10 for this one. That's pretty hard. So you need to experiment with the data. You need to have a somewhat better understanding of your data. The good thing is in the image domain, it's not too hard because images have all typically very similar intensity values. We can even scale images to certain standardized sizes, normalize them in a certain way so that choosing this parameter, at least for the image domain, is not super critical, at least if you want to get somehow decent results. Of course, if you need to fine-tune it and get the perfect last performance out of it, you need to adapt this, but overall, it's not as tricky as it may sound initially. And if your features get very high dimensional, it also gets slower. So it's typically well suited for lower dimensional spaces, less suited for higher dimensional spaces. Okay, so what we have done basically today in the lecture, we are looking into clustering as a task of grouping similar things without having to provide an explicit semantic label. So compared to the clustering, the classification approaches introduced in the last 2 weeks, where you assign to a data point a semantic label and then want to generalize to new data points, here the task was, given our data points, how can we actually generate groups of similar data points, which seems to be somehow related. And there is some relation to this, but the main difference is here we specify basically a distance function or something which will turn into a distance function. And the other one is just a semantic label where you say these two things are the same class and then try to do the same thing. So they are different from the problem. And the problem of getting training data is something that we have in classification, but what we don't have here. And this is kind of this unsupervised form. Unsupervised means I don't need training data. So I just can work with the raw data. Is very popular, and this is a class of clustering algorithms that are used for a large set of problems. So not just for the image domain, what I presented here. This can also be, if you think about the 3D point clouds, you may want to cluster 3D points in your point cloud to identify what are individual objects that you see in your point cloud. Also, one of the popular approaches where clustering is used. Again, for the image domain, mean shift is one of those standard choices. Agglomerative clustering is also something which is very easy to understand, very easy to debug. You can build these trees, at least for, let's say, medium-sized data sets or not too large data sets, where just the distance is displayed. You can nicely indicate the neighborhood between those clusters. K-means, Again, one of the most popular algorithms, although it's less frequently used for pixel-based classification in images, but you can use it for it, but mean shiftability provides better results. And something which I didn't dive into the details today because of time is if you relax in k-means, this indicator variable b to not be a 0, 1 variable, but to be a variable which can take values between 0 and 1, you can do things like soft assignments or soft k-means, where you can say, oh, data points belongs 60% to this cluster and 40% to this cluster. And if you take that a step further, it actually can actually use this to use estimate Gaussian mixture models. So sums of Gaussians if you take, again, a Gaussian kernel or a Gaussian distance function into account. Which then, if you generalize this more, leads you to the expectation maximization or EM algorithm. And therefore, this k-mean can be seen as a special case for the expectation maximization algorithm. But with this, I'm actually coming to the end. And we nicely covered all the topics that we wanted to cover in this lecture. So again, as a repetition, for the next week, I will be here and Nived will be here, and we are here to answer your questions. So either you come with questions, we're happy, we'll answer your questions. If after 50 minutes everyone says, everyone is happy, I know everything, no further questions, then fine, then we're done. So with this, thank you very much for your attention, and it was a pleasure to teach this course. All the presence of all you was good. It's something that I appreciate, and Nived appreciated as well, I guess so. And so thank you very much for coming here, and see you, most of you, hopefully next semester. Thank you very much.